next talk by Lotte. He's going to talk about Haskell for JavaScript.
That's right.
Not in current Haskell in the browser.
Sorry?
Not in current Haskell.
No, I just changed the title. Yeah, I overwrote my title. Anyway, I'm actually going to talk about Haskell in the JavaScript. I'm working on JCGS, Haskell to JavaScript compiler based on DHC, which means we have to find a way to translate all the Haskell data structures to JavaScript. So we're running in a new managed runtime that has its own garbage collector, but that's not used to things like data evaluation or complications that come with that. And in JHC are solved within the JHC storage manager. We have to cooperate and interoperate with the JavaScript one, which is annoying at points, but well, we have to make it work. So first, a bit of information about how GHCDS works. It's a standalone program. Currently, it hooks into the GHC API. GHC does the type checking and optimization in the front end, of course, before, and all the variables in the source code. When the code is STG, which is a relatively small language, slightly heavier than core in GHC, but still relatively easy to translate.
It's a bit hard to hear you at the back.
Okay. There's no microphone, right?
No, that's right. You see,
okay,
manual volume increase.
I'll just talk a bit louder.
There you go.
Right. Normal GHC translates STG to CMM, where it has its own Drupal optimizer with all kinds of fun optimizations. But CMM is really a low-level language that cannot express all the JavaScript object-oriented and other features. So we don't use the GHCGS. We have our own language based on JMacro, which is a somewhat simplified JavaScript AST. We use the GHC API to give us this STG code. We translate it to there, and we do our own rewrite rules optimizing JavaScript code there. And in the end, we can combine that with our own foreign imports. That's where you can add your own JavaScript calls to the code. And in the end, we combine all the code to a single big JavaScript bundle that you can insert into your HTML page and have your really nice type-safe application written in Haskell in the browser. So where we are, since I've been working on this for a while, the code generator is reasonably stable, which means if you have a big program, something like the ICFP contest reference implementation, that used parsec, UU, parsing lib, a few other things. I don't really know the implementation. Duncan said he would make it open source, so I'm looking forward to that. And that worked basically without any bugs. There was one static initialization thing where I had to bump a limit of how big global objects could be, but I think there were no other bugs. So that's more or less where we are now in terms of stability. Last year I lost a lot of sleep trying to get the examples ready in time for my talk at Haskell Symposium in Boston last year. So this year is a bit better. It's also reasonably possible to install it. Duncan managed to do it himself, so if you have more than 10 years Haskell experience, a PhD, then you might be successful. So some of the other people in the community didn't really manage to do it. So, but that's a reasonable improvement compared to last year, where it was probably forget it if you haven't written it yourself. And it's actually still a bit better now, since I think Duncan installed it at a slightly less stable time, since I made some very big changes that I'm going to later. We have Cabal support, where it's mostly complete. We can add JavaScript sources, distributed JavaScript libraries with the Cabal package, just like you have C sources in packages. So it's when these things, it's a separate branch that hasn't been merged yet. I hope to start a discussion about what I've changed that should be made in Cabal to support this soon. But I think we are reasonably close now to something that works in most situations. And this summer, recent additions that we now have cost centers, and based on that, step traces and heap profiling in the generated code, so we can actually do something about memory leaks, see where they come from. Since we translate JavaScript, and Haskell has a very different evaluation model. Okay, I'll talk louder again. Thanks, Simon. So since Haskell looks very different and the code is not idiomatic JavaScript, and there's a reason for that, since that's actually the main point of this talk, it's really useful to have these GHC features, and in particular that you can debug the code and find things the Haskell way, the normal way that you do with GHC. You insert your cost centers in the code and you find out which cost center are leaving memory. That's the things that I was talking about earlier. Template Haskell now runs on Node.js, which means if I have some template Haskell splice, the old version used to load native code, which is basically the same approach that GHC uses. It uses the GHCI linker, or if you have dynamic programs, it can use dynamic libraries. But that means you have to have native code available for everything that might run template Haskell. And there's something else. You have to have native code available for every package that has a custom setup method, since it will have a setup HS script, and it has to be compiled with the compile library. So there's enough support now for that to run all these things on Node.js. Everything can be compiled to JavaScript. You can run it on the Node.js JavaScript engine, which is usually used for building web applications. And it can read files, it can start processes and stuff. So if you have the appropriate bindings for the base library, the process library, and file path, and a few other things, then you can run compiled programs like this to something that you can just run in the shell node. And that made us able to drop native code from a standard installation of GHCGS, which means it's not necessary anymore to have all the build tools and the libraries ready that you also need for installing GHCs. Things like integer GMP needs libGMP at the right location, and this was confusing people, and it was making it very hard for many beginners at least to install it, since, well, you don't tell a beginner to install GHC from source. They should usually install the Haskell platform. And if GHC.js as a package is just as hard as GHC from source, that's not a good thing. So I'm really happy that we can drop this now, since only generating JavaScript reduces all the system-specific dependencies considerably, and this really works well. Template Haskell on Node.js has another advantage. It means that template Haskell has been separated from the GHC process now, and it runs on a different architecture. So the same approach makes it possible, if we merge this back into GHC, to run template Haskell for cross-compiling. If you have a way to run the generated code for the target platform in, say, an Android emulator, then you can just have some small program there that can load some library, run the code required from template Haskell there, get everything back. So I hope to be able to get that back into GHC if there's more interest in that. But I think it can be really useful. And last year we were really bare bones in terms of library, and finally we were seeing some libraries for web things appear, things that make it easier to program with in Haskell with web. Someone last week or 2 weeks ago made some simple game library that uses WebGL and some FRP framework to make it easy to make some simple 3D games that work nicely. There are some basic DOM bindings, some bindings for more convenient incrementally updating DOM things, so you can have web pages that are dynamically updating and efficient. There's still a lot of work to do, especially since everything is based on the JavaScript way, and we have some JavaScript bindings. And it's probably not the ideal way to do this in Haskell, but we still have to figure out how exactly to do it. So there has to be some start. So starting with this kind of library is a good starting point. So just to prove that it works a bit, so last year I had to write all the examples myself, and every example has a lot of work to get going. This year I could just compile something written by someone else. So at this rate I'll probably won't even have to do the talk myself next year. But first, for example, the gloss library is to the graphic library that is simple to write. Some simple programs for like simulation or something with some input. Just a few lines of code. Why is it stopping? It should work. Anyway, this is just an, oh, it still works. It's just, it's almost stabilized. It's a graph-based, a force-based graph layout algorithm. So this is just completely unchanged. It's one of the examples in the gloss examples package. And this uses the gloss backend for GHCDS, which writes everything, draws everything on a web canvas instead of an OpenGL or Glove window that you normally uses. But you don't have to change your source code. So just as easily, one of the other gloss examples I'm lazy. So this is the void example, some flocking demonstration. So if you have written something in gloss and you want to show it off on the web, then just recompile it and link it in your blog post. Much easier than linking to an executable or more accessible than compiling the source code. So someone posted this a few weeks ago on Reddit, some physics simulation that he wrote on at some hackathon or something, and he posted some executables and some source code, and with the comment, in the future GHCDS will be able to compile this, and it's thought, well, future is, I'll just make it talk. So a few days later I had this, I have to admit I have been a bit sloppy updating the bindings for these libraries. So, but it's almost complete now, and it's a cute example. You can, it has some user input, so it shows the future of this thing, and what's going to do something like this, and then if I then restart, I'll shoot this, then it'll run, it will show the future path, and it can still in something like this. Well, good example, and it's also just completely unchanged. So just as accessible as Glut is for making things locally, you can just show them off the same way everywhere else. Well, something more showing off part of the runtime capabilities. This looks really boring, but this is a table with 10,000 cells. Every cell is updated by a single thread that has that does a thread delay of, I think, a random amount between 1 and 10 seconds, and then it randomly changes the color of something. So this is a highly concurrent thing, and it's reasonably efficient. You can have this many threads and just treat this as lightweight threads, just like you do in normal JC, Haskell. And the thread switching is quite efficient. If you know the language shootouts, where you can compile GHC Haskell with many other languages and compilers. There are a few standard benchmarks, and one of the benchmarks that Haskell is really good at is the thread rating benchmark, where you have where you have, I think, a few hundred threads, and you pass the token around many times, and you print at the end the thread ID of the last thread that has the token. And that really depends on having fast, lightweight threading. So Haskell completely dominates everyone else, except Go, which is almost as fast now, but since they have preemptive threads, the requirement is preemptive threads there. But the GHCDS scheduler is pretty fast. So I compiled that program with GHCDS. It was about 8 times slower than native code. But it's not that bad, since if you compare it to all the other submissions, it's still faster than Java, C++, C, and basically only Erlang is faster than the JavaScript thing, and not faster than Java, and also Go is faster, but it's almost as fast as GHC. So it's pretty cool that you can have this kind of concurrency with that's still lightweight enough to actually use it for highly scalable things. You can also do it for I/O, and then it will use the JavaScript I/O manager to do callbacks into from the runtime to your user code, and that user code integrates with the GHCDS thread manager that will wake up threads when some data comes in from the server or something. So it's all really convenient to program. It's a bit of a different programming model than most JavaScript programmers are used to. Like if you read something from the server, you do a request, it's something that you wait some time for. JavaScript programmers will say, I'm not going to block, that's going to freeze the user interface of my whole application, and threads are inefficient. Well, they aren't. So the easiest way to do these things is to create a binding that doesn't really replicate the JavaScript way. It should do something that uses the GHCDS thread model, and well, that allows you to do much more convenient, many things much more conveniently. Like if you want to handle an error, a timeout error or something, or a connection abort error, then you can just throw an exception in the thread. If you do the JavaScript way, you have something that manually does a callback, and there is a continuation that will be called. You have to check an error condition. It's annoying. And other things like doing a timeout is something that requires a bit of special care. In Haskell and in GHCDS, you just say timeout, some IO action, and that the thread manager will, when it's time to time the whole thing out, throw an exception to the thread running the action. That action will be interruptible. You can handle the exception there, so you probably close the connection with the foreign code bindings, and you just go on from there. It's much more convenient to program this way in most situations. So I'm happy that that works. There are a few other things. People ask me if they can compile Haskell to GHCDS to JavaScript. They can't really, but they. I found another cute example. PureScript is a simple language that compiles to JavaScript. It's inspired by Haskell. It has a static type system and a few more experimental features. It has effect types. And I just compiled the PureScript compiler to JavaScript, and well, it works in the background. It starts compilation every time I type something, and when I type something more, it aborts compilation. I send it an async exception, and that makes it completely responsive, even if when it's computing. I can run the program since it's compiled to JavaScript. It's a bit inefficient since it recompiles the whole standard library every time it types something. So that's not the PureScript fault. I was told by the PureScript author that I'm just calling the compiler wrong. So I've been lazy here. And a result that I really like, it's a result the GSO project this year is the profiling. You really come back to the course of this talk. We really want to have good development tools for JavaScript, for programming Haskell in this environment. And in particular in reactive programming frameworks, it's often hard to reason about memory consumption, and sometimes you have leaps of things that you don't force properly when you have some state accumulating somewhere in your program. So we really want heap profiling. This is the heap profiling of GHCDS. It uses the same cost centers as GHC. It has a UI with real-time updating plot. It's a bit of a weird plot since I'm running a computation that's intentionally leaky. It's building a huge stack with and then building lots of things up on the heap. Just some fold L that is strict enough, and depending on whether it's doing one calculation or on what point this heap snapshot is taken, it will be up there or it will be low. So, but this is real time, and we can pause things. There are a few bugs in there, but when these have been fixed, you can select the cost center that you want to extract, or you can filter them. So this should be really useful. At least I'm happy with this, since it's really hard to infer what's really happening and where things are happening from the JavaScript profile, since the lazy evaluation makes things happen at a different place. At least the call stacks don't really make sense. So, and there are other projects, other people have been able to get this going. So Chris Smith has built a web-based playground for working with Haskell, and he wants to teach Haskell and mathematics to children and young people and anyone who wants to learn these things. It's really cool thing. You have some examples you can edit in the browser. And actually we have a working internet connection, so you can write games and move. So it is a cool project. Check it out and help them with this. And it's based on GHCDS. Every time you hit run, it calls the server and it sends you back the JavaScript for the program that you've typed. So, but back to the objects. Let's see. So that's where we are. It works. There are lots of libraries to make programming more convenient. Like we have something like quasi-quote. Oh, that's short. Oh well, do one nice demo, right? We have some quasi-quoting. We still have many things in progress, but I'm working on a new code generator that makes things smaller and makes it more competitive. And that lets you drop some features like this fully threaded model is fairly heavy weighted, increases your code size a bit. But if you can do without, and that's one of the things that I think we really should be working on, if we can make something where, wait, it's the next slide, if we can modularize the base library of JavaScript, of Haskell I mean, in parts that really small Haskell compilers can support, something where you don't need high-level concurrency things, then we can make more compact JavaScript code that can run on smaller devices. And if you have something that supports more packages, then more things, then you can just add dependencies on other packages and have it run more complete Haskell. And in that way, we don't have something that's halfway supported, but something where you can really say, this part is completely supported, you can expect this to work properly, and other parts are something where you have a bit more, require a bit more of the browsers. So heap objects JavaScript, that's a bit short. The main difference between Haskell, between GHCDS and other browsers in translating things to JavaScript is that GHCDS does its own translation, its own translation of closures and environments to JavaScript, which means everything in compiled GHCDS code looks like a JavaScript object. And JavaScript objects are things that you can inspect from JavaScript. So you can see everything that's reachable from Haskell, and you can actually make these heap snapshots from the Haskell runtime. And that also makes it possible to do many maintenance things that GHC does, like reading out indirections, supporting weak references, seeing what cache global values are reachable and deallocating them, removing many memory leaks. So, and that's really useful. It makes memory consumption in GHCDS much more predictable. Unfortunately, I showed the demos a bit too long, so I can't really go too deep into detail. But we still have to skip to the end because everything is traversable. We know what's going on the Haskell heap, but it's a bit inefficient to actually find out. So there are a few things that we can do differently. Some things where we can take a shortcut, and we really want to take as many shortcuts as possible. Since if we wait a bit too long doing some cleanups, the JavaScript garbage collector will already run some garbage collection. If you leave some data reachable for too long, then since all these engines, even Firefox, have generational GC, then objects will get copied, they will get more expensive to collect. So the main thing I'm working on and finding out is how to make sure shortcuts, doing things as early as possible, trying to do things not the GHC way, but the way that does something better. Sorry for not listening. Any questions or is it fun for that?
So we have a couple of minutes of questions.
How do threads actually work in the browser? Do the browsers have threads for JavaScript?
No. Haskells do have web workers, but those are more or less processes. You can't really, there's no shared memory. You can start and you can have some IPC. There is some way to migrate objects from A to B, but they are far too heavyweight, at least as far as I found out, to implement for objects. So these are not used. One of the side effects of the heap representation we have is that we can inspect computation. So it's still possible to serialize a computation run with all its references from the heap and send it over, which is more than something like Cloud Haskell can do. But it's still a very explicit operation, so it's something that's not suitable for productions.
What is required to make this a backend flag with GHC? So like it's a GHC-F JavaScript. That's all this stuff.
To make it the backend, well, it depends. I don't think it's all that hard. I think in Cabal there should be some changes that accept the same compiler but with different flags. Since the flag will affect the package database, the JavaScript package database will be distinct. Other than that, I think it's mainly a question of finding out whether this is really the right way to go forward, if there are other ideas that we should incorporate and have it stabilized. So I think we can, if we really want, get this merged, but something like in a really experimental status. But I don't really want to be too quick with that before it's clear enough that it's ready. But I do agree, if we are able to split up the base package and have something in the Haskell ecosystem where we can say this is really supported and have that also optimized for the browser. Things like libraries are written for native code now, and many people, including you, are responsible for adding inline rules everywhere. So something that's happening is if you look at last example, if you have data.sequence, and that's used by Sodium, a FRP framework, the native code for that, if you add up the total size of the native code for the object files, is 1.5 megabytes. You have split object linking with GHC and the same kind of approach in GHCDS. But you still find out that just by using this module, or this single module from the statistics that it generates, adds a few hundred kilobytes of JavaScript to your program. You can still minify it. It will be a bit smaller, but it's really heavyweight, and I don't think this is necessary. So there should be some review of these things. And Cabell has in the current patch a different field for GHCDS options that override GHC options. So perhaps something like optimization options can be different for GHCDS, or you can have rules that can be slightly different from there. But I do think 1.5 megabytes is probably not that good for the instruction cache on native code either. So some gains are there.
Thanks again.